Well, good morning. This is a little after 11 on Thursday, the 7th of September, 2017. This is supposed to be Linear Algebra, Math 237, and I'm the only one in the room, which is not a good sign, but hopefully the others will be coming. I did want to remind, and I'll probably say it every time someone comes in, but if you're listening at home to this, reminding you that on Tuesday I do have a doctor's appointment at 10 o'clock in the morning, and I'm hoping that he's through with me by 10:15, which means I should be able to be back on campus by 11. No guarantees. In fact, the odds are I'll probably be a little after 11. The point being, I will be back as soon after 11. If I can be here before 11, I will, but as soon after 11 as possible. I should be back here on campus, so please, if I'm not here right at 11, stay right here. I'll be here just as soon as I can, okay? If you wanted to and you have a computer, or if your phone will do it and you want to look at the YouTube video that I did where we end today before we start on Tuesday, you can do that, but I should be here pretty soon. I doubt if you would need do it, but you certainly are welcome to. So, still waiting for someone to come in. Hopefully, one or more of you will get here before too long, okay? Because I hate talking to myself. Okay. So, just marking in the book something I noticed I had in my grade book, something I had forgotten. This out of order too. I was grading papers in between classes. And here comes somebody. Jasmine is here. Good deal. Okay. I was just saying on Screencast-O-Matic before you came in that reminding folks who if you were listening at home, didn't make it today, catching up, that I will not go out. I've got a doctor's appointment Tuesday, but I should be back on campus sometime around 11. There's a real good chance it may go a little late, and if it does go late, I might be a little later than 11, but I will be here. So come Tuesday, don't leave. If I'm not here right at 11, I'll get here as soon as I can. Hopefully it'll be shortly after 11. All right. Any questions on anything we've done till now? Okay. Then I have that we were in Chapter 1, Systems of Linear Equations, on Section 1.2, Gaussian Elimination and Gauss-Jordan Elimination, and we're 21, and this was the bottom of the page. What's this again?
When do we need to turn in the topic before I exit?
Anytime you can.
Okay.
Yeah. Okay. That'll be great. Okay. Actually, I'm not in this class, but in some of my other classes, I've already actually received essays. So anytime you want to, get them in as soon as possible. Okay. Near the bottom of page 21, sorry about my throat, sort of cloggy today. Theorem 1.1. The number of solutions of a homogeneous system. So here's the deal. A homogeneous system now. Every homogeneous system of equations is consistent. How do we know that's true? Yeah, because the trivial solution, every variable equals 0 will always solve a homogeneous system, okay? So there's the first part. Every homogeneous system of linear equations is consistent. Moreover, okay, so that's the first part. Let me get my pen activated here. Okay, theorem 1.1. Okay. Every homogeneous system of equations Now we're talking about linear equations. Okay, is consistent. Now what do we mean by consistent? That it has at least one solution. So therefore we know it's consistent because that one solution, trivial solution, every variable equaling 0, it will solve every homogeneous system. Okay? But the moreover part, if the system has fewer equations than variables, okay, then it must have infinitely many solutions. Okay, it must have infinitely many solutions. Now, if it has fewer equations than variables, it must have infinitely many solutions. Because you know it has one, and if it has fewer equations than variables, it's got to have an infinite number. Now notice what that doesn't say. It doesn't mean that if it has more than equations and variables, it will have only one solution or anything else. That's not the case. It's just that if it has fewer than equations and variables, it must have an infinite number of solutions. Even if it has the same number of equations and variables, you can't conclude anything from that. Okay? But if it has fewer, it's got to have infinitely many solutions. Okay? And they talked you through how to do a proof of that using sort of like example 9, but you do it for the general form. And that finishes 1.2. Sorry, that was the last thing we had to do in 1.2. So homework exercises here, any of the odds 1 through 5, I've assigned most of these before, either 7 or 9 or both, any of the odds 11 through 17, any of the odds 19 to 23, any of the odds 25 to 29, 25 through 37. Do number 39. It's the only one like that. Now, that's a big, long, hairy, massive problem. It says use a graphing utility or a software program if you've got it. If you don't, you can still probably at least start the thing, but if it gets too bogged down, just let it go. Okay? Do either 41 or 43 or both. Do 45 and 47 and 49. Well, let's see. Let me back up a minute here. Yeah. Do 51, 53, and the rest of those is up to you. 55 is just a sort of a think-through type thing. 57 is a true-false, has multiple parts to them, but think through those too. 59, all the rest of them are just things you can think through and do. You don't have to turn in, you don't have to, you don't have to turn any of them in. You don't have to actually physically do, unless you just want to get a little bit better feel and understanding of it. All right, any questions on 1.2? Okay, let's move on to 1.3. This is applications of systems of linear equations. And generally, I skip this section. It's a great section, but we are a little behind. But it is something that you might run into sometime, polynomial curve fitting. Not a bad idea to read through that, especially if you think you might need it in the future. So I'll let you decide that. But that's one application of linear equations. And they have, let's see, 4 examples of that. Another Okay. There is a little blurb at the bottom of page 28 on applied linear algebra, and talking about researchers from Italy studying the acoustical levels from vehicular traffic at a busy three-way intersection on a college campus, and they use systems of linear equations to do that. So they have a paper there. You can go and look at that. Now, another one is network analysis. And what is your major, by the way? Mechanical engineering. You may actually do something like that in mechanical engineering, but it's more likely to be things like computer science or possibly industrial management or industrial engineering. You could easily have network analysis. Again, worth taking a look and just see what you got. But one place I almost guarantee you'll run into that is Kirchhoff's laws, and this is in electrical. And I know even though you're mechanical engineering, you deal with electrical systems. Your physics, you're going to have Kirchhoff's law, so let's do Kirchhoff's laws. This is on page 30. Have you already done them? Oh, what were you going to say?
So this is applications of linear algebra.
Right. Yeah. But you can read about the others, but Kirchhoff's law is, in a sense, kind of like network analysis, but it's a very special types of networks. Okay? Electrical network is another type of network. This is on page 30, a little above midway through the page, where analysis is commonly applied. An analysis of such a system uses two properties of electrical networks known as Kirchhoff's laws. So since we're using his laws, you could even, if you chose to, write on Kirchhoff, okay? But his laws might be a little bit more appropriate subject, but you can do either one, and you don't have to do either one. But here is two laws. All the current flowing into a junction must also flow out of it, okay? That's pretty key. Whatever you got coming in, you got to have going out. You can't pile up charge at a junction, current at a junction. The second, the sum of the products, and they say IR, for I is current, R is resistance. What that means is the voltage drops, the sum of all the voltage drops around a closed path is equal to the total voltage in the path, in that path, okay? And they give a few of the symbols here. I'll write those down for you since you don't have your book in here. When you see on a circuit diagram a symbol like this, that indicates a battery. Two cells of a battery. Usually under here they'll give you the voltage of that battery. Okay? Another thing you'll see in a circuit is a jagged line like that. That's a resistor. Okay? And we usually represent the current in one direction or the other, and usually conventional current would flow the opposite way. This will be the current, I. So this will be a voltage, this will be a resistance, and that's a current. And voltages and currents and resistors are related by V is equal to IR. Okay. Now, let's do the example 6, because I know have you taken physics yet, or are you taking it now? Okay, is that mechanics or electricity and magnetism? Physics 1? Okay, that's mechanics. In physics 2, you'll do electricity and magnetism. So next term, if you take it here, you'll be doing Kirchhoff's law at some point. Probably, maybe not quite midway through, but it won't be at the very beginning, but it'll be somewhere in the term. Somehow I got something stuck in my hair. What world is that? I thought I was feeling something. I don't know, it may just be a tangle, I don't know. Alright, I'll worry about that later. here is your circuit. I'm going to start in the upper left here. There really doesn't have to have a corner there, but that's how we usually draw it. Going to the left from here, we happen to hit a resistor. Okay? And they tell us that resistor, they name it R1, is equal to 3 ohms. The unit for resistance is ohms. Okay? You keep going until you hit a battery. Okay? And that's a 7-volt battery. Okay? Now, just a little bit of indicator here. It's plus 7 going in that direction, minus 7 if you go in this direction. Because you're going from low potential to high potential. That's positive, from high potential to low potential. That's why they put unequal bars so you know which way the current's going. Okay? So, you hit the battery. You hit the end of this and go down here. End of this and goes down here. All right, here's Kimmel. All right. Now, I said this earlier twice now, but I'll say it again since you may not go back and listen to the YouTube video. Just a reminder, next Tuesday I do have a doctor's appointment at 10 o'clock. I'm hoping I'll be out of there by 10:15. No guarantee. That doesn't usually happen, but I'm hoping I will. If I get out by 10:15, I can almost guarantee you I'll be back here by 11 for class to start. Okay, I can't guarantee that either because traffic, they're doing construction on the interstate, all that kind of stuff. So I can't guarantee that either. But that's what my hope is. Now, if either I don't get out of the doctor's appointment at 10:15 or traffic's bad coming back, I may be a little after 11. But I will be here. Okay? So if you get here at 11 and I'm not here, stay. Okay? Okay? Now, if it gets really, really late, I will call somebody and have them come up here and tell you, look, I'm not going to make it. I can't foresee that happening, but it could happen. I sure hope it doesn't happen. Okay. But be here. I will be here if at all is possible. Now, I also said this before you came in. If you want to, if I'm not here and you have either a phone or a computer and you want to start looking at, figure out where we left off today and start looking at that on the last time I taught the course on the YouTube video for that. It's out there on our playlist. You just find the last one we did here and do the next section of what's coming up after that. You can kill time doing that, and then when I get here, we'll just pick up and go from there. Okay? Or not if you don't have this. Okay. What we're doing is Kirchhoff's law. This is a network analysis. This is in 1.3 applications of systems of linear equations. Okay? Here we reach a node, and they call it number 1. I'll continue that and call it 1. From here, going to the left, you hit another resistor. They call this R2, and they say R2 is 2 ohm, a 2 ohm resistor. Okay? And that goes all the way to node 2 here. Okay? Then down here in this leg, we have another resistor, cleverly named R3, and they tell us this is a 4 ohm resistor. Okay? And then you hit another battery, big side here, small side there, and that battery, they tell us, is 8 volts. All right. Now, they name 2 nodes here. Now, notice this isn't a node because you don't have one wire coming in, one wire coming out. It's not even a bend there. I mean, you can make that a curve. It doesn't matter. This is a node because you have either 2 coming in and 1 going out, or 2, some way you have a junction there. They also call these junctions. Okay? And Kirchhoff's first law says the current coming into a junction is equal to the current leaving the junction. That's one way to say it, okay? Or the sum of the currents coming into a junction is zero. It's another way to say it. The second law says the current in any closed loop, not the current, the voltage in any closed loop, voltage dropped in resistors equals the voltage increase in battery, okay? That's another way to say it. So usually what the good thing to do here is to make a guess on which way you think the current's going, okay? That's a good guess. Now, don't worry if you guess wrong. If you guess wrong, then you're going to come up with a negative current. If you have a negative current, just say, oh, it went the other way, okay? So it won't hurt to guess wrong, okay? It'll correct itself at the end. Well, I told you before, if this is a positive current, it's going from low potential to high potential. So a good guess would be that here is your current loop in the top one, and going from low potential to high potential, there's a current loop in the bottom one, okay? And these two are going in the same direction, so that sort of makes sense. Okay, so let's name this to be I1. I think they already do this for you. Well, they don't put a direction on it. They do that to be I1, this to be I2, and this to be I3. Okay? Now, with those, that is a very ugly arrow there. I can't even tell which way that's supposed to be pointing. And I drew it. Okay. I3 is going in that direction. And I2, of course, is going in that direction. I drew it right under the arrow. Okay. So those are our three currents, or at least where we suppose they are, in the direction we guess they are. And we may be wrong, but it doesn't hurt to have something to start with. Okay. Kirchhoff's first law, the total current going into a junction is equal to the current coming out of the junction. Well, here's a junction. This I3 is coming into the junction. That I1 is coming into the junction. So I1 plus I3 must equal I2 because that's the current going out of the junction. Okay? So there's your first equation. Oh, and what it's asking for, we're looking for the currents. That's going to be our answer, what the current is. So here's an equation. I1 plus I3, well, wait. No, I'll put it this way. Plus I3 is equal to I2. Okay? Now, that is certainly true. The sum of I1 coming into the junction and I3 coming into the junction is equal to the sum of I2 leaving the junction. Okay? Now, that won't make a very nice linear equation because that's your unknown. Those are your variables. So we want to get them in order. So let's rearrange that ever so slightly to be I1 minus I2 plus I3 is equal to 0. You buy that? Okay. Now, let's go to node 2. Node 2 has I2 coming in, I1 going out, and I3 going out. Well, that would be I2 is equal to I1 plus I3. That's the same equation. So you don't get any new information out of it. Don't bother with it. Okay? It turns out being the same equation. Okay, so those are the two, that's the junction rule. Now let's do the loop rule. Okay? Now I drew two loops there. There was a third loop we could have done. I drew them because that's what the book had. You could have drawn a third loop. This one would have been harder to guess. That could have been the outer loop. That way. Because guess what? We're going around. But these two make more sense. So those are the two. We only need two more equations because you only have three unknowns. So let's use those two. Now, again, I'm going to write down as I read it. Let's start right here at this point in the upper loop. So I'm not going to use the outside loop. I don't think, unless I have to. I don't think I'll need to. Okay, we'll start here. Let's go in the same direction of our current. So what we have is an increase of voltage of 7 volts. Okay? Then we have a decrease in voltage minus 3 I1. Remember, your voltage drop is I times R. R1 is 3, I is I1. So that's minus 3 I1. Continue around here, and now you have another voltage drop of minus 2 I2. I2 times R2, that would be minus 2 R2. That's the drop as well. So you have minus 2 I2, okay, and you're back to where you started, so that's equal to 0. That's one way to do it, or you could put your I's on one side and your constant on the other side, and that would give you 3 I1 plus 2 I2, no I3s there, okay, and that's equal to 7. Okay, there's a second equation, okay, from one loop. So let's do the bottom loop, okay, and again, I think I like to start at the corner down here and go up the battery first. So that's going to be an 8 volt, okay, and then you have a drop in current minus 4 I3. I3 times R3 is 4 I3. That's a drop in voltage, and then you get up here again and you have another minus 2 I2. And that sum is equal to 0. The loop rule says that total voltage around the loop is equal to 0. Or the voltage supplied is equal to the voltage drop, which is the way we would do it the second way, which would be 2I2 plus 4I3 is equal to 8. All right? There are 3 equations in 3 variables. How do you think we're going to solve those? Using linear algebra. Make a matrix. Very good. Okay. I'm going to do it here just so I'm afraid I'll need the room. So what's our augmented matrix that stands for that? 1. This one.
Are you going by?
Yeah. Yeah.
1, 1.
That's the negative one, isn't it?
1, 1, 1.
Okay.
3,
3, 2, 0, 7, 0, 2, 4, 8. All right. Now, just looking at that to begin with, what would be your first step?
Okay. You need that 3 and that second
Okay.
row becomes 0.
All right. He's jumping right into what you need, and that's a very good thing to do. You got a 1 where you want it, and you want that to become 0. That's all right. Okay? So you're absolutely right. However, mostly because I'm used to looking at these things, I see something here that I can immediately simplify.
Yeah.
What?
Divide 2 by.
Yeah, all that is divisible by 2. So let's simplify and make that a 0, 1, 2, 4. You okay with that? Okay. So I'll make this a 1, 2, and 4. I just don't have a lot of room, so I'm going to do it now. 1, 2, 4. Okay. Now, I'm back to where you were. We want that 3 to become a 0. How do we make that happen?
3 R1 plus.
Minus 3.
Yeah, minus 3 R1.
R1 plus R2. Got it. What does that be? Oh, we're using row 1, so write it down. 1 minus 1. 1 and 0. Okay? What's your new row 2?
0.
0. 5,
negative 3,
negative 3,
negative 7.
no, 7, 7, yeah. Okay? And the third row is just what we want, 0, 1, 2, 4, after we change that, of course. All right. What do you want to happen next?
You want to get that 5 become a 1.
That would be ideal. Now, the only way to make that happen, divide that row by 5, right? Is that the easiest? Okay, wait. Before you do that, why don't we flip those two? Rather than introducing a bunch of fractions here, if we flip these two rows, you got the 1 where you want it. And remember, you can exchange any two rows anytime you want to. So this will, all I'm going to do is row 2 and row 3 exchange. Okay? So this will be 1 minus 1, 1, 0. 0, 1, 2, 4. See, that's one reason I went on and did that, so we could do this. And 0, 5, negative 3, 7. All right. Now what?
Get that 5 become a 0.
You want the 5 to become a 0. Now, I've got a question for you, and either answer is right. What you sound like to me you're doing is Gauss elimination. And then we're going to do back substitution. Okay? But you could also do Gauss-Jordan elimination and not do back substitution. It's up to you. Gauss-Jordan. Okay, Gauss elimination. Leading 1, 0 below. Leading 1, 0 below. When you do that one thing you're saying now, you've got it Gauss elimination. And then you, whatever you have here is equal to that. I mean, this is I3 equal to some number. Okay, you get that answer. Then you do back substitution in here to get I2, back substitution in both places to get I1. Okay? Now, Gauss-Jordan elimination would, you make that a 0 and this a 0, and then you make that a 1 and that a 0 and that a 0, and then you just read off. I1 is equal to whatever is there, I2 is equal to that, I3 is that. So you don't have any back substitution today. It's pay your money and take a choice. It really doesn't matter. You choose.
Sound like you're saying Gauss-Jordan is the easiest.
Gauss-Jordan's a little more work on the front side and makes it easier at the end. Gaussian elimination is a little bit easier on the front side, but you have more work to do at the end. So, whichever you choose to do. What would you like to do? Doesn't matter to me. Gaussian with back substitution or Gauss-Jordan without? Gauss-Jordan? Okay. Then it doesn't matter what order you do it, but since we're going to be doing, why don't we go on and make this a 0? How would we do that? Yeah, row 1 plus row 2. You might say row 2 plus row 1. It doesn't matter. Okay? So let's do that. I think I'll need to be down here. We're using row 2, so write it down. 0, 1, 2, 4. Okay, and what's our new row 1 then? 1, 0, 3, 4. Okay. And then what were you telling me to do to row 3? You said you wanted that 5 to become a 0. How do we make that happen?
5R1,
Negative 5, not R1, R2. Plus R3. Okay? This thing is such a pain in the neck. So what does that give us? 0, 0, Okay.
And negative 3.
It's at the bottom. It's negative 5 times 2 would be, yeah, that's negative 13. Okay, big number.
Negative 13.
Yeah, it's a negative, yeah, negative 13 again. Very good. All right. Now what do you do? What's the next thing?
I'll say go ahead and divide negative 13 by 1.
Exactly. Okay, divide everything in the third row by negative 13, which makes it 1, 1. Okay, 0, 1, 1. 0, 0, 1, 1. So rather than divide, I'm going to, because I don't have much room, I'm going to just make that a 1, 1. Okay, that was easy. Okay, and since you chose to do Gauss-Jordan, you got 2 more steps, but we can do them right now on the same thing. And right now, by the way, you know already what I3 is. 1 amp, right? And you could stop and do back substitution if you wanted to. Doesn't matter. But if you want to do Gauss-Jordan, what would you do next? What do you want happen here? Yeah, you want the 3 to become a 0 and the 2 to become a 0. So what can you do to row row 1 using row 3? I can't talk. Second? Right. So let's do that. We're using row 3, 0, 0, 1, 1. Okay. What's your new row 1?
Yeah, 0.
No, not 0. 1. It's minus 3 times 0 is 0 plus 1 is 1. Okay. 0. 0, and that would be 1, okay. And then what are we going to do to row 2? Negative 2, row 3. Goodness, that's an ugly 3. Sometimes the pen doesn't erase too. Goodness, it's still not erasing. There we go. All right. Negative 2R3 plus R2, row 2. This is such a pain in the neck. Okay, writing on a floppy screen. Okay, so let's do what we told it to there. What do you get? 0, 1, 0, 2. All right, let's see. Yeah, perfect. Okay. All right. Now, what can you read off of this? What's that? Okay. Here it is up here. Your variables are I1, I2, and I3. So this is 1, I1 is equal to 1. I2 is equal to 2. And I3 is equal to 1. These are current, so they would be in amps. I1 is equal to 1 amp. I2 is equal to 2 amps. And I3 is equal to 1 amp. Okay. Now, fairly easy to check. Coming in here is 1 1 plus 1 is 2. That works. Goes up 8 volts. Drop 3 volts. That gets you down to 5. And then down here, you've got, no, 7 volts. I can read them right. 7 volts. Drop 3 would be 4. And then drop another 2 times 2 ohms, 2 amps. 2 times 2, that's 0. Sure enough, back to 0. Let's do this loop. Up 8 volts, down 4 volts, because it's 1 times 4 is 4, so that would give you 8. And then you go up 2 times 2 again, that's 4. It gets you back to 0. Sure enough, that works. Okay? So 1 amp, 2 amps, 1 amp. Good deal. Are they all this simple? Dream on. Okay. Nowhere close. Let's do example 7, which is just a little more involved. Okay? Putting it mildly. Here is, coming down here, you hit a battery. Low potential, high potential. And they tell you that's 10 volts. Okay? Continue going south, and you hit a resistor, and they number that R1 is equal to 2 amps. Okay. This is I1 here in that direction. Goodness gracious. Where's what? Oh, current. I stands for current. The current in that first loop and the first side over here. Okay. Go this around and you can hit node 1. Okay. Go up from node 1 and you hit another resistor. They're going to call this R2. And R2 here was 4 amps. Oh, goodness. Where did pi come from? 4 amps. Okay, and you go up here and hit node 2. All right. From node 2, let's move to the right, and you hit another battery. Okay, going up in voltage, and that'll be a 17-volt battery. Then you hit an R4. You haven't hit R3 yet, but we do hit R4. And R4 is 2 ohms. Okay. My ohms don't look very good. It's 2 ohms. Okay. By the way, they call this current, ooh, goodness, it does this every time, I2, going up that way. Okay. Going across here, since this is R4, we also call this I4, going through that resistor. Okay. And that leads us to node 4. You go south on node 4 until you get another resistor, and that's R3 is equal to 2 ohms. Wait. No, there's R5. Here's R3 down here. Okay. This is R3. I'm having trouble reading this fine print here. is 1 ohm. Okay. I can't believe I did that. And y'all let me get away with it too. R2 was 4 ohms. And, okay. Oh, man. I think I was talking about I2 at the time and I was thinking amps. I don't know. Okay. I3 indicates, at least here they show I3 going in this direction. I don't know if that makes sense or not. I haven't. No, it doesn't. Sorry. I couldn't read my thing there. I3 goes through there, but we haven't designated a direction yet. Let's hold off on that. This over here was, there's R4, this is R5. And R5 is 2 ohms. Okay. 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 I didn't show I5 here. Knew I was missing something. And we haven't picked a direction for that yet either. They have, but I'm not going to follow that yet. Okay? Let's do our last leg over here. That comes over here to another battery, high side, low side, and this is a 14-volt battery. And you come down from that and hit a R6, which is a 4 ohm resistor. Okay, and they have I6 here. Okay, now I've just got to make sure I've got everything in here. We got I1, I2, I3, I4, I5, and I6. Yeah, got them. And we got resistor R1, 2 amps. There's another one. Goodness gracious. My eraser isn't working. I know. This is a pain in the neck. Okay. That's ohms. Okay. 2 ohms. If my... Okay, that's the thing. I've shown current 1 here. That makes sense. And current 2 there. Okay. Here's current 4 here. And since there's my voltage there, I think current 4 is going in the right direction. Current 6, I'm going to say, is going in this direction. Okay? Now, where would current 5 be going? It looks like to me it would be going in that direction. And current 3, I think pretty much is to be in that direction. Okay? If you're wrong on a current, don't sweat it. It'll come out with a negative and you just change it. Okay? So, okay, let me check that. I forgot to put that note in. R4 was 2 ohms. Okay? And R3 is 1 ohm. R2 is 4 ohms. R5 is 2 ohms. And R6 is 4 ohms. Okay. I'm sorry? Yeah. Okay. I think I've got it all now. Now, you could have several loops. The easiest loop to follow, I think, are these. Here's a loop. Here's a loop. And there's a loop. And the reason I kind of like those is this has these going in the same direction here, and these going in the same direction here. But you might have more if you need it. You have 4 nodes or 4 junctions. but you can't guarantee they're all going to be independent of each other. The currents, or the loops, I think can be pretty safely assumed to be independent of each other. Okay? But we've got a total of 6 currents, so we're going to need 6 equations. Well, let's start with the junction. The junction is usually the easiest to write. And here we have I1 leaving here. Here's I1, so it's going this way. It's the same thing there. So this is I1. I'll just put it again there. So leaving, oh wait, let's start with junction 1. Coming into junction 1, again, this is I1 coming in. Okay. It's continuing to go through here. So at junction 1, you have I1 coming in, I2 going out, and I3 coming in. Okay? You see that? I1 is coming in, I2 is going out, and I3 is coming in. So you have pluses for those, minus for that. Now you have to have all 6 currents, so the rest of those are zeros. 0 I4, 0 I5, 0 I6, and this is equal to 0. There's your first equation. Let's go to junction 2. Junction 2 has I1 going out. You see that? That's a minus I1. I2 is coming in, and I4 is going out. Whoops. Okay, and the sum of all the currents is 0. Okay, let's go to junction 3 down here. Why they numbered them this, I don't know. Seems crazy, but all right, you have I3 going out, so that's a minus I3. You have I5 coming in, plus I5, and you have I6 going out, minus I6. And that's equal to 0. You see that? I haven't left enough room by a long shot. Okay, let's go to junction 4. It has I4 coming in, so that's plus. I5 going out, and I6 coming in. That's equal to 0. Now that looks like 4 equations with 6 unknowns. I can't guarantee you those are all independent, but we can keep them. Nothing wrong with that. If some of them are not independent, you're going to wind up with a row of zeros and move it to the bottom. Okay, now let's do the 3 loops we get. I know we don't need 7 equations, but I don't know which 6 we need, so let's do those 3 we've got there. Okay? Now, since we know these are our constants, the batteries, okay, then let's do the voltage drops here, here, and here in that loop has to add to this. So we're going to make this a positive and that's a positive equal this. So that way we have positives here. Okay? So this will be I1 R1, which is 2I1. So there's your loop 1. We'll call this loop 1. This was junction 1, junction 2, junction 3, and junction 4. Now for loop 1, okay, it's going to be, we know our constant's going to be 10, okay, and what we have here is 2I1, and here we have plus 4I2, That's equal to 10. That's all we've got in that loop. Let's do the middle loop. Okay? Now again, if you follow this along, you have a plus 17, so that's going to be your constant. And then all your others are going to be drops, but we're going to put them on the other side, so that will make them constant. And just because let's keep our numbering right, here we have 4I2 plus I3 plus 2I4. Those are your voltage drops here. Oh, oops, I missed one. Plus 2I5. That had 4 resistors in it. R2, R3, R4, and R5. I didn't put them in order, but I put them in the order of our variables up here. 4I2, 1I3, 2I4, and 2I5. Okay? I don't have enough room. Okay. I'll have to make a big matrix down here. Okay? Our third loop, this is loop 2, loop 3. This is loop 2, loop 3. Okay, the 14 volts going to be over here. That is the increase. Your decrease is just going to be 2R5 plus 4R6. Okay. So, I'm going to write my system of equations here. I've got 7 equations. I'm going to write them in matrix form. That first one here, the junction 1, is going to be a 1, minus 1, 1, 0, 0, 0, 0. Right? You got 6 currents, so first 3 you have. Junction 2 gives you minus 1, 1, 0, minus 1, 0, 0, 0. You tell me.
No.
Oh.
L3.
L3, yeah.
What's that again? 14.
Oh, goodness gracious. You make me read my writing? Okay. It's R5 times R times I5. So 2I5. 2R, that's the I5, not R. I think I wrote R's. Glad you caught that. I don't know if that's what you're asking, but it's a good catch. Those are I's there, not R's. Goodness gracious. 2I5 plus 4I6. Okay. 2I5 plus 4I6. Okay. Would have caught that next, but so let's do junction 3. Zero. Negative 1. 0. 1. Negative 1. 0. Got it. Next, junction 4. 0. 0. 0. 1. Negative 1. 1. 0. All right, let's do loop 1. But let's be smart about it. What are your coefficients? 2, 4, and 10. Guess what? Divide that by 2. Right? So I1, that would be a 1, just so I don't have to write any more than I have to. I2 would be a 2. And then you have 0, 0, 0, 0 for I3, 4, 5, and 6, and that would be a 5. Got it. Loop 2, don't think there's anything we can simplify. So that would be a 0 for I1, 4 I2, 1 I3, 2 I4, 0, 0, and 17. And then look at the loop 3. What do you notice there? By 2. Okay, so it's 0 I1, 0 I2, 0 I3, 0 I4, 1, 2, and 7. There are our 7 equations with 6 unknowns. So we know at least one of these is not necessary. We just don't know which one. Okay? Now, unfortunately, I need a lot of room to write, so I'm going to have to erase my circuit. So I hope you got it. So, it's in the book. You can always go back and see it. But I'm going to have to erase it so I can start my work. Okay? And these are a pain in the neck to erase because there's so many little marks around them. Okay. Wonder how this looks at home. I think I've seen it before. It looks rather weird. Things just start disappearing. Okay. So what do we want to happen in our matrix? Okay. The 1 is just like you want. You want that to become a 0 and that to become a 0. So what's your... I'm going to write down the first row. 1 minus 1, 1, 0, 0, 0, 0. Okay? And you want that minus 1 to become a 0, so how do we make that happen? Row 1 plus row 2, right? So what does that give you? 0, 0, 1, yeah, 1, negative 1, 0, 0, 0. All right. Then the next 2 rows are perfectly fine. You got zeros in both of those. Now we go to row, what, 1, 2, 3, 4, 5. What do we do here? Yeah. Yeah. How do we make that happen? You know, that's doable. That's a legal move. I was going to use row 1, but you can use row 2. So it's fine to do it that way. Row 2 plus row 5. Row 2 plus row 5. I was going to do minus row 1 plus row 5. That's easier to do. Just make sure you keep them together. That gives you a 0, 3, 0, negative 1, 0, 0, 5. Okay, good choice there. Next, the other rows are fine. What did I just do here? I forgot to write my other rows in. Sorry, I have to go back and I can't leave them out. Okay. Let me write in row 3, which is 0, 0, minus 1, 0, 1, minus 1, 0. Write in row 4, which is 0, 0, 0, 1, minus 1, 1, 0. Now my new row 5 was, remind me, 0, 3, negative 1. No, yeah, you're right, 0. I was looking at the wrong one. Negative 1, 0, 0, 5. Got it. Okay? And the next two rows are fine too. 0, 4, 1, 2, 0, 0, 17. Oh, what a fun one. And the next one is 0, 0, 0, 0, 1, 2, 7. Okay, I sure hope I got it right. All right, what's the next thing we want to happen?
You want that 0 in the second row to become a 1. Or
Okay.
you can change that 3 to 0.
Okay, let's backtrack. What we want to happen is the first non-zero entry in this row to be a 1, which looks like it would be okay, except we have a non-zero entry that's in the second column here. So what we have to do is either swap these two rows or swap those two rows. I mean, we have to move a row around, okay? Now, to get this, you're going to have thirds here, minus 1/3 and a 5/3. Okay, that's not bad. If you did this one, this would become a 1/4, a 1/2, and a 17/4. Which would you rather have? Thirds or fourths? Neither, but we got to have one. Pay your money, take your choice. Second? Thirds, okay. So let's move this up to row 2, okay? And just drop the others down. Is that all right? Because that's a 1. I like that 1 being there. I don't want anything else. So I'm just going to drop the others down. Okay? Now this is going to take a bunch of writing, but it's doable. So I've got room to do it here. Okay. So what I'm going to do, I'll just do it with an arrow here. I'm going to move this up to row 2 and drop everything else down. Okay? So this becomes 1 minus 1, 1, 0, 0, 0, 0. Okay? Now, new second row, and I'm going to go on and divide by 3 at the same time. Is that okay? 0, 1, 0, negative 1/3, 0, 0, 5/3. Is that okay? Because I need it to be a 1, not a 3. Okay? Now drop everything else down. My new third row is going to be what was my second row. 0, 0, 1, minus 1, 0, 0, 0. Yeah, okay, good. I was afraid I messed something up there. My next row is going to be the 0, 0, minus 1, 0, 1, minus 1, 0. Now my next row is going to be the one with the 4 in it. 0, 4, 1, 2, 0, 0, 17. And my last row is going to be the 0, 0, 0, 0, 1, 2, 7. Okay. I'm going to have to lose my loops here. Okay? Is that okay? Hopefully we've used them. By the way, this course is brought to you by the Paper Manufacturing Council. Okay? Because you have to use a lot of paper on that. All right. So what have we got? We got a 1 there with all zeros below it. Fantastic. A leading 1 there. And it looks like we're going to need to, you want to do Gauss or Gauss-Jordan?
We're working on we'll focus on that 4 now.
Okay, yeah. That certainly we got to get this to become a 0. The question is, are you going to mess with that one or not? Yeah, it's easy enough to do. So at least do that. So what we're going to do is
Negative 4R1 plus R6
Not R1, R2. Negative 4 times this one. And add to that.
I thought, okay.
Yeah. And then I'd say first, let's just add these two rows together to get rid of that. Okay? All right, so the first thing we're going to do is row 2 plus row 1. Okay? All right. So the new row, I'm going to write down row 2. 0, 1, 0, minus 1/3, 0, 0, 5/3. All right.
Yeah, you're missing the row. You're missing the row.
Where?
We're missing that 5th row. We didn't switch it.
All right, let's see.
Yeah, right here, we're missing.
Yeah.
We're missing this row. Well, I know you divided that.
Yeah,
We didn't
now
break
this
it.
one went up there. Okay, so I'm still probably missing one. This should be my 3rd. That should be my 4th. Ah, it's the 5th row I'm missing.
Yeah.
Okay, so yeah, let me put that in there. Where is it? There it is. It's the 1 above there. This is a 0, 0, 0, 1, minus 1, 1, 0. Sorry about that. Okay. There we have it. Okay. And don't let my crazy looking zeros make you think it's a 4. That's a 0. Okay. So our second row is what we're using, and we're going to clean out the minus 1 above, which would be add row 2 and row 1. That's pretty simple. 1, 0, 1, negative 1/3, yeah, boo hiss, 0, 0, 5/3. Okay. Then the next 3 rows stay the same. 0, 0, 1, minus 1, 0, 0, 0. 4th row, 0, 0, minus 1, 0, 1, minus 1, 0. The 5th row, which I tried to leave off before, is now 0, 0, 0, 1, minus 1, 1, 0. Okay? Now, we got to get rid of this 4 here. And like you said before, minus 4 row 2 plus row whatever that is. 6. Yeah. So let's do it. That will give me a 0. That will give me a 0. So minus 4 times 0 is 0 plus 1. That would give me a 1. Minus 4 times minus 1/3 is positive 4/3 plus 2, which is 6/3. 4/3 plus 6/3 is 8/3, I think. No, 10/3, isn't it? Goodness gracious. Let me go again. Okay. Minus 4 times this plus this. That would be a 0. That would be a 0. Okay. That would be a 1. That would be minus 4 times that is minus 4/3 plus, and this is a 2. So that would be 6/3. So 4/3 plus 6/3 is 10/3. Okay. This one, yeah. Okay. And then that would be a 0, a 0. And that would be minus 20/3 plus 51/3. Yeah, minus 20 thirds plus 51 thirds will be at 31 thirds. So I think that would be a 0, and a 31 thirds, I think, okay? And write down the last row. 0, 0, 0, 0, 1, 2, 7. Okay. All right, got to erase my junctions here. Now guess what? These things can get tedious. And it seems like to me, I probably just skipped this one last time just to keep from having all this to do. Because I don't remember going through this agony before. Okay, I mean, this exercise before. Okay. Probably erased too much, but it's okay. All right. Now, what do we want to happen next? We got a 1 at the top and 0 below. 1 in the second. First non-zero entry is 1, 0 above and below. And we got the next one being a 1. So we need to get the ones above to be a 0 and these to be a 0. Right? So, we're going to use row 3. So down here, there's row 1, row 2, row 3. I'm going to write row 3 in here. 0, 0, 1, minus 1, 0, 0, 0. Yeah, got it. Okay. Now, I want that 1 to become a 0. Yes. Negative R3 plus R1. Okay? So that's going to be a 1. That's going to be a 0. And that's going to be a 0. Right? Got it so far? Okay. So negative a minus 1 is a plus 1, which is 3/3, minus 1/3 is going to be a 2/3. And then we'll have 2 zeros, and then a 5/3. Right? All right. Second row is perfectly fine, so we'll write it down. 0, 1, 0, negative 1/3, 0, 0, 5/3. Okay? The fourth row, we want that minus 1 to be a 1. Be a 0, right? So basically we add row 3 and row 4, right? Don't we? Row 3 plus row 4 will make a 0 there, won't it? Okay, wait. We're using this one, add to that and make this one.
Oh, okay, yeah.
Yeah, we want that to be this one. Okay, see, we got that row 3 already in there. We're not going to change it. Okay? We're changing our row 4 by adding row 3 to row 4. So that'll be a 0. Next will be a 0. The next will be a 0. The next will be a minus 1. And then you'll have a 1. And then we'll have a minus 1. And then we'll have a 0. Did I do it right? Okay. All right. That's the fourth row. The fifth row, I think, is just what we want it to be. 0, 0, 0, 1, minus 1, 1, 0. Is that right? Okay. And the sixth row is 0, 0, 1, 10/3, yay, 0, 0, 31/3. I hope that's right. And then the next row, whoa. No, wrong. That row we wanted to change. Okay. Cause,
Can we go ahead and add row 4, row 5, and become a new row 4?
okay.
Can we go ahead and do that?
Okay. You mean these two?
Yeah.
Yeah, and this is going to become a row of zeros.
Yeah.
And then it's going to go to the bottom and we don't have them anymore.
Wait a minute,
Yeah. You see, when you get a row of zeros, if you add those two together, the bottom row becomes, this row
wait,
becomes.
wait a minute. Can we switch? Can we switch those 2 rows?
Okay, yeah, we will. Yeah. We'll do that next, okay? Yeah, we want to do that. What I'll do, I'll make this a plus and minus a plus. Leave it alone, okay? And then this row wipes out, because you see, if you add these 2 rows together, you get all zeros. And that I said we had one more row that we needed. You'll wind up with a row of all zeros. There it is. And then we'll be down to 6 equations, 6 variables. That will be like we want. What I forgot here is we're using this 1 here, and that 1 there, we need that to become a 0. And that's why I started writing it down. So no, that's wrong. So what we can do, like you did before, is add these 2 rows to make that a 0. You want to do that?
Row 4 plus row 6?
Yeah, row 4 plus row 6. Okay? So let's do that. Row 4 plus row 6. That's your technique. Okay, row 4 plus row 6. Okay? So doing that, we get a 0, a 0, a 0, a 10/3. You had to come up with that, didn't you? 1, a -1, and a 31/3. Okay? And then the last row is perfectly fine. 0, 0, 0, 0, 1, 2, and 7. All right. Now, using what you said and what I said, okay, you wanted to switch these 2 rows, and I said we're also going to add them together. So basically, it's going to wipe out this row. So let's just do that. And then you'll have that 1 where it needs to be. Okay. So I'm just going to wipe out this row all together. Okay, that became...
How will we write that?
You add the 2 rows together, it becomes all 0, move it to the bottom and lose it. Okay. Yeah. All right. Now, that gives us 6 equations, or 6 rows, so we don't have to worry anymore about those. So I'm going to get rid of this because I don't have room for it anymore. And are we out of time? I think we've been out of time for a bit, haven't we? Okay. Why don't you take this home and finish it? Okay? And let me know what you come up with. Okay? And because we are out of time. Sorry about that.
And so, wait a minute. So is that it? And then start doing.
No, not yet. Okay.
So
Then this moves up here. All right. Yeah. Let's get our strategy down. Yeah. This moves. This is here. Okay. We'll need to eliminate that. Let's multiply this row by minus 10/3 after that row. That's going to mess things up there, but I think it'll be okay. And then you'll have your leading one there. I'll be real suspicious if we don't swap these 2 rows, and then we'll only need one thing to eliminate. Yeah. So we're really close to being through. Okay. Yeah, and we really want a lot of zeros. Okay, now, wait. I didn't quite say that right. We've got these to become zeros here too. So this is going to make those 3 zeros and that a 0. Okay. Then I'm pretty sure that we want to flip these 2 rows and have this leading 1 there. And then this will be down here. You'll eliminate this and whatever you have above it, which isn't much. And then you'll finally eliminate the last one. And it really, we've got the bulk of it done. You've got quite a few operations left. But when you write the next one, just leave this row out altogether. And you're fine. Eliminate this and those. Like these zeros and that a 0. Then I'm pretty sure the next thing you're going to do is flip these 2. And then you'll make whatever wind up here, make that a 0 because it'll be below it then. And then with that last row, take it off. So it seems like a pain in the neck, but it's really on the short rows now. Huh. If you don't get an answer or the right answer, don't sweat it. They said use Gauss-Jordan elimination or graphing utility or a software program. I'm really wishing I had a graphing calculator at this point, but we're almost there, so we could do it. So we'll leave that. You finish. If you don't get an answer, let me go and give you homework exercises here. We're basically through with 1.3 when you do that. Any of the odds 1 through 11, then do any of the odds 13 through, oh, wait. Back off. We didn't do any polynomial curve fitting, so don't worry about 1 through 11. Okay? In fact, I'd say the only thing you should worry about here, let's not do any of those until you get to 31 and or 33. Do 31 or 33. That's all you have to do in this. And those are much simpler than the one we're just working on.
31, 33, and 160.
No. Say, no, okay. Back off. Don't do any of 1 through 13.
Gotcha.
Okay. Don't do any of the first. All you have to do in 1.3 is either 31 or 33 or both. And they're both pretty simple problems. In fact, they're very similar problems. Okay? All right, good deal. And we'll be through chapter 1, and what I'll do is I'll have ready for you next time your first test. It'll be a take-home. What's that? Yeah, if you got it ready, I'll take it. I'm sorry I went over.